So I think we can start. I will mute you right now, just in case you want to have a voice or whatever. I will switch to chat so you can ping me there, and I will unmute you. So let's go this way. Yep. Okay, guys. So it's as follows. First, today it's about the networking. I don't know how experienced are you with the networking, but I will just give you a full course, full introduction on to see how it's. How is it? Generally, IoT is Internet of Things, right? So the Internet is the word that says it have to be networking here. Otherwise, we just talk about the embedded systems. So networking is the core for this stuff. And as we say, IoT without data transfer is not an IoT. Actually, it's just a lonely device put somewhere in the middle of nowhere doing some local activities, and that's all. So all about the IoT is transferring data forth and back, sensing, then transferring into the local storage, then perhaps putting it over the network, pushing it to the cloud where you can make some knowledge discovery. But it also works in the opposite direction. I mean, from right to left. This way, the data sensed goes to the cloud. Once you have some knowledge here, then you can make some actuations. So for example, if you consider something like a smart house or a smart home, you may, for example, sense there is rain comes. So, for example, because of the cloud are around you, or it starts to rain, or it starts to be windy, or you have a forecast, even saying that I said there starts to rain. So you send this information to some computing center. It says, okay, it's time to close the roof windows because no one wants to get a flood inside, and it returns back with information for you to make an action on the actuators. Please don't think about this cloud and the knowledge only as it's, for example, the Google, Microsoft, or IBM Watson. It's not true. You can have it locally. The cloud solutions are available, for example, for your local NAS like QNAP or similar, or even the Raspberry Pi with some storage and computing resources could be your small cloud at home. We are talking about the general structure here, how it goes. Okay, so just to be from the very beginning, when we start, at the very low level, you have some sensors. And the first is just to send the information from the sensor itself to your computer, to your local nodes, which is actually in this case usually single chip system on chip, like ESP, Atmega. Could that be ARM with some external memory in this case? But generally, there is a number of the protocols you can have here. So the first one is, and the most popular is SPI and I2C. They are digital protocols. They're rather for the short distance. Well, theoretically, I2C can be up to 100 meters with a very slow 500 hertz, but this is not the purpose. The purpose is just to send a message from the sensor to the development board or to NPU and eventually send back an actuation. Right? We are talking about the different protocols already, but here is just like a summary of what you can have. So first of all, for short distance, yeah, it's SPI, I2C. For the long distance, it could be any of the very popular COM. RS-232 stands for the industrial COM. Whatever you know about that, this is the most popular protocol in the computers. I believe it is dated on something like 1970, 1960 even. Those RS 423, 422, 485, they're industrial, well, obsolete. Still, you can find them. You can find the interfaces on the AliExpress, in the shops. Even I have seen a couple of them in the shop in Latvia, which is close to the university. That can implement that one. It's very popular in the automation control systems for the heavy industry, like coal, mine, iron, all this stuff. You can find still the machines talking in RS-485 and also RS-232. The distance up to a couple of hundred of meters, even up to 1 kilometer possible. And there's also one protocol you use frequently in your solutions, isn't it? It's called CAN. This is mostly in automotive industry. Most of the cars dated 2000 and younger, they have this CAN interface between the different processors available on board. Many of the cars are even have it embedded on the very unusual spaces. I can recall my Renault Laguna had backlight connections over the digital line, which was actually really surprising. Not just a wire switching on and off, but just the two wires coming to the back integrated lamp and the decoder that was responsible for switching it on and off. Pretty surprising. Anyway, here is a short summary what you can have. So in case of this RS232, the most popular one, it's like a one-to-one connection. This is like an advantage, but also disadvantage. You connect one device to one port. It means if you want to have a couple of sensors, you need to have a separate ports or do the multiplexing, switching between things. The maximum data rate for the longest connection is really slow in this case. It's 20 kilobits per second for some 4,000 feet. However, we know that when we connect the device, the regular connections are 9600, 11, 15,200, which is the most popular, for example, for uploading the firmware to your microcontroller. And eventually they are higher, up to close to 1 megabit per second. It's 9 something, if I can recall right now. Only the most modern ones support that one. On the other hand, RS485, for example, is up to 4,000 feet. 4,000 feet is well, divided by 3, you will have a meter, so it's like a 1.3 kilometer, close to 1.3 kilometers. Of course, for this distance, it's slow. For a short distance, you can go up to 10 megabits per second, which is pretty good. If you consider the CAN bus on the right-hand side on the table, you still have different lengths. Also depends on the speed. In the case of the car, you get the lines up to some couple of meters from the bonnet to the back. So this is usual. In case of the robots, it's same. It's just a couple of centimeters till 1-2 meters. That's all. We do not use, however, CAN very frequently in IoT. It's rather limited to the autonomous systems. Yeah, it happens there are interfaces, but they are not very frequent. Most of the sensors they talk about. I talk about like an environmental sensors. They are related to SPI or I2C. Now, if we consider the distance and the purpose of the different protocols, you can think about like first you have a very short distance ones. We call it personal area network. And the personal area network is when your mobile phone talks to your headset wirelessly, or if you have, for example, a Mio band on your hand just to control your mobile phone, or eventually you have some heart rate monitor on your chest, or just like a smartwatch talking to your mobile one. So this is personal area network. It's like limited to yourself, limited to a couple of centimeters up to 1-2 meters, no more. The good example of that one is Bluetooth. Right, that's perhaps one of the most popular protocols in the world. Now, local area network is what you have at your university, at your home. So this is like a still short distance connection. We say that, for example, Cooper-based Ethernet is up to 300 meters, 305 exactly. Strange why this line, but like a single spindle of Ethernet you can have, it's about 300 meters. So this is up to one connection. Of course, depending on the cable, you can have different speeds, class 5, class 6, and some variations. The higher the class, the better the insulation, electromagnetic insulation, so the higher the transfer speeds for this distance. Of course, you can have a shorter. Then you have something called like a metropolitan area network. All those networks, they have a different standards. Perhaps you know that for the PAN it's 802.15. For the LAN it's 802.11, like this Wi-Fi, you know, pretty popular. For the metropolitan area network, it's fiber channel ones. It's IEEE 802.16, and for the wide area network, also fiber channel, it's 802.20. They are the standards you can look for, but actually it's not very important in this case. Now, if you consider the length of the distance, so you can have a really short distance communication, like a printed circuit, a couple of millimeters, a couple of nanometers, even up to a couple of centimeters, or just the size of, this development board, for example. Later on, we have a short distance communication, and can be like an NFC ANT protocol, which you know, for example, from the Garmin watches. RFID, which is actually the pretty interesting case. And RFID is like a passive communication, which means that you don't need to have a powered transceiver. Receiver, yeah, and the receiver sends enough energy over the air to activate and charge the RFID tag, and to let it emit some radio communication back. It's usually just an identifier, so you have to grab energy from the air. Other communicators like an NFC, near field communication, the one from the mobile phones when you pay at the shop, or you use your smart card like a Visa or MasterCard just to pay. It's NFC then. And a number of the protocols that perhaps you have seen or heard. It's like a Z-Wave, Zigbee, and the 6LoWPAN. We'll talk about the 6LoWPAN a little bit later on. UWB, it's one widely used for indoor positioning. You know it well, I guess, from your lab. Bluetooth, Wi-Fi, and a number of the different protocols related to the GSM communication. Here we talk about a couple of 100 meters up to a couple of kilometers. Of course, depending on the generation of the network, of the GSM network, the higher the generation, the smaller the cells are. So, for example, 2G and the 3G has a much longer distance than 4 and 5. The 4 and 5, there are small cells just to handle more devices at once, to have a higher transmission speed, but for the short distance. Later on, we can talk about gigahertz frequencies that we use, for example, for the GPS communication and the satellite communication, up to actually geostationary orbit. It's 36,000 kilometers one way, so it's pretty far distance. So this is what you can have regarding the networking of the classification. Now let's go into the details a little bit. A couple of the principles. First of all, IoT devices, they share internet with these large machines, like with your PCs, with your Mac, with your servers, with the powerful mobile phones, with the mainframes, all those stuff. So they need to find a way to integrate those two worlds. And the IoT devices are usually very limited, very constrained in the resources. The principle of the sensor network is just to measure something and work on the battery for weeks, months, or even years, right? On the other hand, you know pretty well how many times you need to charge your mobile phone daily, and even if you extensively use the network, like a Wi-Fi and data transmission, then you know that perhaps you need to charge it twice a day, isn't it? I think so. So in that case, there are some glitches here between what the IoT devices can do and the fact that they need to interface the internet infrastructure sooner or later. The solution for that one is a protocol translation that is done in something we call a fog layer or a proxy layer. This fog layer is a layer of the devices that they collect the data from the IoT sensor networks and the actuators eventually, if they work opposite way. They reroute it to the internet, to the cloud, to the public cloud, for example, or the private one located somewhere in the internet. But they do protocol translation, and they provide some extra information that the regular IoT devices cannot do because of their constraint things. Actually, this difference, this border here is disappearing slowly because the technology is developing so fast that even those low power devices are capable right now to talk, for example, in the full TCP/IP stack, like, for example, this ESP 8266 or ESP32 in SPACIF. However, Still, you need to keep in mind that perhaps the purpose is a little bit different. So there is no reason or there's no way you can implement full internet stack, right? Anyway, even in case of the IoT communication, the IoT networking stack, it follows this ISO-OC stack. This ISO-OC stack, if you know it, it's a stack of the layers where the data has been transferred vertically from the application layer in the very top into the physical layer in the very bottom. Forward and back depends on if you are sending the data or receiving the data. And virtually every layer is independent on the other. So you can, for example, exchange Wi-Fi to Ethernet, as you do, right? You have a converter, so you have an access point at home, so you have no problem just to send information from your mobile phone through Wi-Fi to your router and then to route this communication into the Ethernet to your provider. You are doing this at the moment, watching me perhaps, I guess. Here we have this layeret also in the IoT solutions. Now, here on the left-hand side, you can observe the typical protocols for the regular internet. So if you go from the bottom first, at the very bottom, you have a media access control, MAC. It comes from the media access control. And the PHY, it's physical. So those two layers, they're like a low-level layers. At the very low level, you can have, for example, an Ethernet or a wireless, I mean Wi-Fi here. On the top of them, there is a network layer built of the IP protocol. It can be IP4 or it can be IP6. And then the transport layer, which is TCP or UDP. And then the application layer protocols. And the most popular one, perhaps, is HTTP, right? You know it well from the web. Whenever you go, you will use perhaps an HTTP JSON. One of the still pretty popular protocols is file transfer protocol. It's FTP, but there are really, really many others. Now, on the right-hand side, you have an IoT smart devices stack. And this smart devices stack is still using this layeret model, but please look into the differences. First of all, at the very bottom, you have a different physical media access controls. It can be like, for example, regular RF on 433, 868 megahertz, or 915 in case of the United States. You can have a Bluetooth. You can have long-range wide personal area networks. And many, many different. However, on the network layer, the protocol of choice that was especially designed for the IoT is 6LoWPAN. 6LoWPAN is like an extension of the IPv6 for the IoT devices. We'll talk about this later because this is a really interesting one, so I will show you how it works. Now, at the top of it, you still have a TCP and the UDP. And at the very top of it, you have a number of different protocols that are solely for IoT, or actually they share from time to time with the real world. We'll talk in this lecture, but not today, but next week. We'll talk about the MQTT and COAP protocols. It's like my choice because I found that they're the most popular ones, and perhaps you will use them in the laboratory. However, as an interesting thing about the MQTT, I wonder if you are using Facebook. I guess so. How is it in case of Latvian students? Are you using Facebook or are you not?
Well, depends on the person.
Yeah, really.
Okay, I know it. It really depends on the students. Facebook is a little bit very long already in the internet. Okay, but you definitely know how the Facebook Messenger looks like, isn't it?
Yeah.
Okay, so interesting thing is that Facebook Messenger uses IoT MQTT protocol. Of course, right now, because of the performance, it was optimized. But the very, very beginning, when they started, it was using like a plain MQTT. So you will see it later on how this protocol is constructed, and then you will understand how it works. So I'll welcome you today for the next week, because the next week we are going to talk about the application layer protocols, which is actually more useful from the developer point of view. But I want you just to study this physical layer first. So let me. Oh, I'm sorry, just unmuted you. So let me go through the quick review what you can have in the IoT world. Okay. So here we talk about the media access control and the physical layer all together because they are usually integrated. So first, perhaps the most popular in case of the many manufacturers, early manufacturers of the IoT devices, let's call it smart devices for smart homes. The protocol was called ZigBee. Well, actually, the ZigBee breaks this classical stack. I will show you it on the next slide. How is it constructed? But it is like the father of the or the mother, whatever. It's the father of the IoT communication. So it's worth to mention here, and it's still working. You can have a ZigBee interfaces, ZigBee radios still with these. ZigBee is great because it delivers out of the box routing of the messages through the different devices. So, for example, you don't need to have a cover of the network for whole your home. It is enough that, for example, your window can talk to your door and broadcast the messages through your door, through another door, perhaps downstairs to your access point. It works this way. Real nice. The natural that comes to mind when you think about the wide area communication is GSM, isn't it? It's almost everywhere. Yeah, I know. I still, for example, my parents live in the area where it's barely covered, but it's pretty unusual. Let's say 99% of the humans are living in the area where the GSM is available. Unfortunately, for the IoT, it's a little bit problematic because of the two reasons. First, you need to pay for the service. And if you have a device that, for example, is supposed to wake up once a day, send you some message, and then go sleep, for example, some measurements, then you will never get a good contract for it, right? As no one is interested in providing an optimized contract for, let's say, sending one SMS per day, and so it's 31 SMSs per week, right? So they will charge you a lot of money. And if you consider the scale of the IoT systems, even in single office building, it can be 1,000 of them. So right now it means huge money. Now, it is a solution where you have no other solutions. Let's keep it like that. Now, RFID is just for the identification. We call it like enabling technology. Enabling technology for the IoT. But this RFID, as I said, its future is that you can have an ID read without necessarily having a device powered. It's really nice, however, it's really limited. So this way you can only expose the identity of the device, but definitely you won't be able to send any measurements. So it's just for the ID. Near field communication, well, yeah, but it's close to contactless cards, so the distance is really some couple of centimeters. Narrowband and broadband PLC could be a solution here, and maybe some dedicated services like an SMS or the cellular networks one, right? So it still works. Now, this is IoT ecosystem. As I found it a year ago when I was preparing this lecture. So you can see that the impression I would like to remember is there's a total mess. As you see, physical layer and the data layer, they used to be all together. So, for example, this one is the standardization for the IoT. It's 8.2, 15.4. But there's also Bluetooth Low Energy. There's also Wi-Fi. There's also third and later generations of the GSM. At the top of it, on the network layer, there is an IPv6. Somewhere in the middle, there is an 6LoWPAN. Here in the top of that is ZigBee, parallel to the TCP and the UDP, and also HTTP that you know from the internet, and for example, COAP and all the other from the IoT. So there is no standardization actually at the moment, and finding out the correct solution is really state of the art. So you will struggle perhaps with choosing an appropriate protocol depending on your situation. here you have a sharing regarding the different distance. So you can refer to this lecture later on. I will share it with you, also the recording of this video, just to have an impression where to look for the protocols, what you can have, right? So you can just choose them. Now, just to show you what is actually the problem with the IoT and node devices is information about an implementation of the simple stack using a tiny operating system. This is the smallest operating system in the world. So the core of the system is just less than 1 kilobyte. Implementation of this IoT physical and media access layer less than 10 kilobytes of storage, right? And on the right-hand side, you have a RAM necessary. Communicating UDP over 6LoWPAN is about 5 kilobytes, right? And here you have some higher level protocols. So as you see, the oldest solution is something about 50 kilobytes or even less. 50 kilobytes, not mega, not giga, but kilobytes, right? So there are the constraints we are facing. Now, if you get lost in this stuff, I would suggest you to follow this guideline. First of all, if you have some low performance devices, like an Arduinos, ESPs, maybe some Sony controller, I not necessarily mean the chip itself is not powerful. It could be, but you have a low battery resources, and this is like your main constraint here, right? You cannot go 24/7 full power, full connectivity because of the lack of the energy to do that, not because of the lack of the computing power. So I would go to something like a 6LoWPAN then. Eventually Wi-Fi and Ethernet, if you can have a connector, right? You know, there are like an Ethernet shields for Arduino. You can connect them to the wired network. The protocols of choice is an MQTT. That's called Message Queuing Telemetry Transportation, or COAP protocol. And they are the two mostly widespread in case of the heterogeneous systems. Well, homogeneous systems, they do have different solutions, like this from Somify or other vendors that are closed, but they have their separated solutions and they are not licensable. You need to pay for the license, or even they won't let you have an access to the documentation. So there do exist different IoT protocols, but they are not open. We are talking about the open stuff here, how to connect your device and integrate it with the system, okay? On the right-hand side in the green, if you have some Raspberry Pi, like fog layer devices, this medium performance devices, then you can go to the regular IP stack. Indeed, Raspberry Pi, or for example, NVIDIA Jetson, this Nano Jetson, I mean, this is usually the device that acts like first choice of the fog layer or proxy devices. They usually interface Internet on one interface, like an Ethernet one, and on the wireless one, they constitute a gateway or an access point for the IoT network, for this constrained IoT network. So this is like we used to solve it. Surely you can have binary streams here. Raspberry Pi can handle pretty good video communication, and if you consider the machine like this NVIDIA Jetson Nano, which is actually no bigger than the Raspberry Pi. I just wonder if I have one here to show you how it looks like. Oh, it's not very big, but it's pretty impressive. Now, just trying to find it out. Not sure if I will succeed. Okay, promise you to show it later. But anyway, this device is able to handle the communication of up to 8 full HD channels parallel. Pretty good. I mean, not only communication, but also video processing. So in that case, you are really facing powerful devices, like, for example, gigabit communication. Still nothing special. You can have even more interfaces. You can extend them using USB or PCI connectors with some other radio interfaces. So that all works. Now, how frequent is an IoT communication then? Well, there's no answer here. Look, you can have, for example, the scenario where you have volcano monitoring and you send the data when something happens. If you're in Iceland, perhaps it happens like a couple of times a year. If you're living in Yellowstone, could it be as well, right? Maybe in Kamchatka. But if you're living in other areas and you're observing some, like, for example, Vesuvio, perhaps the alarm will be raised once 1,000 years, something like that. Huh? Okay, that was actually a very unusual example, but anyway. You can have like a medium frequency, for example, reporting of the traffic lights or switching the traffic lights. Right? It happens every couple of seconds. But you can also have it like very frequent in millisecond time, or even quicker if you, for example, consider some industrial solution where you have some valves, you have some flow measurements, and you need to report every couple of minutes. For example, imagine you are mixing some chemicals that that can blow if having non-appropriate components or consistency. What is the distance? Well, we already discussed that a little. It could be like your left pocket talking to your right pocket. So, for example, from your smartwatch to your smartphone. Or it can be like a global, right? Imagine a network sensor that do exist in Iceland. It monitors most of the hills, most of the volcanoes that are actually spread over all the country. So it's like pretty big solution. Or you can have it, for example, for monitoring the movement of the glacier in Greenland or in Himalayas. So one thing is in IoT is very special. This is something we call enrollment challenge. If you consider that you, for example, have a building of 60 floors, it could be even more in Hong Kong or in Singapore or in Dubai, right? So the question is, how do you create a network by individually booting every single device, providing it with the credentials to connect to some access point, and how to do it in the mass scale? The answer is, well, you can't. You need a different solution to do that. So the best would be that the network would self-organize itself. And this is something we call a mesh network. We'll talk about the topologies in a minute, but generally the mesh network is something that we consider to be a network where the devices are able to join the networks, of course, safe way. We'll talk about the security of the networks in 2 weeks from now, or in 3 weeks, we'll see. But generally, what I'm trying just to tell you is that it is different. It's not the case when you install Windows on your laptop and then you provide the credentials to access your Wi-Fi. It doesn't work this way anymore. We need something special, and that's coming. Now, let's go through this physical layer, wireless communication first. In case of the Wi-Fi, we generally use 2 frequencies. Now the third comes, but this is like a special one. But the regular one is 2.4 gigahertz, which is the oldest one, and the new one is 5 gigahertz. The great thing is they're unlimited in use. The only limit from the legal point of view is transfer power. They have a slightly different spectrum in different countries, so this is the reason why when you first configure your access point, they used to ask you which country you're in, because the radio needs to behave a little bit differently depending on the country regulations. That's usually embedded into the firmware. There are major differences between, for example, United States and Europe and Japan and Asia. The transfer speed you can have is some between 2 megabits per second up to a couple of gigabits if you consider the latest AC standard, or if there are even the newer standards that are not yet commercially available. However, the bad thing about the Wi-Fi is there is no centralized controller for the physical access control. So if the collision occurs, for example, 2 devices start to talk one to another on the same frequency, they talk to the access point. You will have a glitches, right? And you need to solve it. There's a protocol called CSMA-CA, This protocol works the way that if it detects some collision in the transmission, then it breaks and it repeats again with the random access binary exponential increase, repeating over the time. It is like when there are two devices and they detect the collision at the same moment, the deal is just not to let them all start to repeat it in the same moment of time, right? So they have to make some differences in the time when they start to repeat. Usual configuration is one center or one router or a switch or access point and clients connected to it. If you even consider, for example, the EDROM, that's at your university and it's mine, and you may think about this, okay, I have a lot of access points, but actually you're connected only to one of them. If you need to move from one building to another building, then you switch from one router to another router. So it's still like the network topology is kind of the tree, and at the very end, the tree is like a star. So the center of the star is an access point, and you connect the devices to it. And in this model, the only communication is one-to-one. So one device talks to one channel in the access point at a time, and your Wi-Fi is never talking to other access points parallel, right? Unless you have more Wi-Fi interfaces. But single interface is designed to talk only to one other. Now, another protocol pretty popular for the IoT is Bluetooth. Up to version 5, or actually up to version 4.5, the only topology was something called scatternet. The Bluetooth generally was considered to be piconet. Piconet means up to 8 devices, where the single device is a master and the regarding devices are slave. Let me explain you. In the Bluetooth, there's always one controller. We call it master. You not necessarily need to think about it like a mobile phone is a master, for example. No, it's not the case. But for one piconet, there is always one master. And the other devices that they connect to, they are called slaves. And the way it works is as follows. The slave cannot initiate the transmission itself. Only master can ask a slave to transmit the data. So master is like actively asking the slave devices if they have something to be transferred. For example, do you have something for me? Yes, no, no. Okay, go to the next one, right? Do you have something for me? Yes. Okay, so get it to me, and so on. So here, master is M, like an N1, M3, M2. A single piconet is 7 slaves and 1 master in this case. However, mind that the master can act like a slave, also parallel. So the Bluetooth is interface, not everyone, but most of them, are working like a double ways, also like a master, also like a slave. And this way you can introduce a routing and you can build a network that is actually something just we call scatternet. Interestingly, the slave can also have a multiple interface, so it can talk to 2 masters at once. This way, you can see it here on the right of this diagram, like slave 23 and the slave 31 is like the same device. So you can share this device among different scatternets, right? Still, single scatternet is like a tree-like structure. Now, from the physical point of view, it looks as follows. Bluetooth goes over 2.4 gigahertz, same like a Wi-Fi. And it has 79 channels. And differently to the Wi-Fi, I didn't tell it that, but in Wi-Fi there are also channels. So they're like a sub-frequencies of this 2.4 and sub-frequencies of 5 gigahertz. But your access point is usually bound with single frequency. So it may be chosen automatically based on the scanning what are the nearby frequencies and choosing the one which has lowest noise, but you do not change the frequency during operation. However, in Bluetooth, it can change during operation if there is an inference. So we call it hopping frequency or frequency hopping. It means that it can jump from one frequency to another frequency if needed. Now, one channel supports up to 1 megabit per second. Around 700 kilobits per second is for use. This is the reason, for example, you cannot have a very high quality audio transfer. You still can have a stereo profile for the communication, but it's limited to less than 1 megabit per second. So you cannot have like a very high quality, high definition audio, only just a regular stereo. The new chips are able to transmit around 2-3 megabits per second, and this is for the latest implementations of the Bluetooth. You still can have it, but it's not like a backwards compatible with all of them. So the regular services are like up to 1 megabit per second per channel. Now, what is interesting is Bluetooth is universal, so you have something we call profiles. Perhaps when you connect your headset to the mobile phone, you will have two. The first is like this high definition audio, and the second is like HSF, HPF. So it's like interface for headsets like the one I'm using at the moment, but the wireless one. So you can have both ways transmission. This is why it's low quality. It will have a mono transmission to hear, but you can also speak. So the channel is like 700 kilobits per second, switched by two, one for the transmission one way, one for the transmission the other way, and you cannot use them parallel, right? So this is how it works. But there are many other profiles. Like for example, if you have touch sensors here, there's another communication standard, AVHCP, audiovisual. Something, well, whatever, generally commands. You can send the commands like a play, stop, volume up, volume down, all those things, right? So it goes also. And there is really a dozen of those profiles. And it grows, but generally the two profiles we are talking about is making a packet-based communication for networking, which is called NDs. And also serial communication. Bluetooth has a profile to encapsulate regular COM, like an RS-232, over the Bluetooth, over the radio. Now, how far you can go? Well, there are three classes in the regular Bluetooth. There are three classes of the devices. Class 1 is up to 100 milliwatts. Class 2 is 2.5 milliwatt, and Class 3 is 1 milliwatt. With the class 1 and the extended data rate, you can go theoretically up to 100 meters, but it depends really on the environment. If you have other devices close, like an access points, Wi-Fi access points, other Bluetooth devices, it drastically goes down. You will never ever have 100 meters here. So 100 meters is something like in the middle of the nowhere, when there are no interferences and the antennas are in the correct position one to another. Now, the Bluetooth 5 that started 2017 fall, and it's already implemented in many devices, including mobile phones, that brings in new quality. We call it mesh networks. This is the network when the device virtually talks to many devices parallel, and they are like a different profiles of the devices constituting this network. Some of them can be like end nodes. Some of them can be low power nodes, like the low power node can go to sleep and wake up periodically to send the data. Some of them are always on, like for example, the relay nodes, and the relay nodes are those who are transferring the data from one to another. They're like a core of the network. But here, the structure of the network is distributed. It means that virtual devices compose themselves, this network, and they do not. It's not a priori stated how the network looks like in case of the Wi-Fi, right? You have in Wi-Fi you have a star network. You connect to the particular access point, and this access point is routing to some other device which is provided for you by the operator and so on. Here it's not the case. The devices talk to one another just to constitute the network. If part of the network is down, for example, imagine that this one goes down, then the devices can go, for example, this way around here just to access the other devices using routing, or maybe the other way, or even dynamically reconfigure the network as needed. So this is really great. But still, implementations are not very popular. We are like 3 years from the standardization, or 2.5, and there are barely good implementations of this mechanism. Now, there is some special new one called the Bluetooth Low Energy. You know it well already. And the BLE is for the state machine representation. Comparing to Bluetooth, it is rather for exposing the state, not for transferring the stream of the data. So this is really great for the devices that they enable from time to time. Examples? Well, for example, a a weight that can measure what is your weight, or just, for example, announcing something from my smartwatch from time to time. This is also Bluetooth Low Energy. The distance is short, it's a couple of meters. From the technical point of view, it still uses 2.4, but it's trying to 2.4 gigahertz, same like a Wi-Fi. But it's trying to minimize an influence between Wi-Fi and Bluetooth Low Energy by trying to hit between the channels of the Wi-Fi. So the peak of the Bluetooth is between the channels. There are 3 advertising channels and 37 communication channels. It's different than in the regular Bluetooth. When the regular Bluetooth, you had just 79 channels and the devices were like talking one to another and making the broadcast. Here you broadcast like one of the 3 channels. It's similar way that the way you use a CB radio. There's one channel just to announce, and if you want to talk to a person longer, you switch to another channel just not to use this advertising channels. Here you have 3 advertising channels and 37 communication channels for Bluetooth. And finally, GSM. Okay, whatever you think here is like there is how it was developing over the years. We are assembled to the 5th generation that is hitting right now the market with a huge objection from the society, considering the health because of the frequency and the radiation. But anyway, regardless of those, please remember that you need to have a SIM card and contract just to use it. And moreover, interesting, if you consider that the typical network era runs out in about 10-15 years, it is less than expected lifetime of most of the IoT devices. That is 15 to 25 years. I mean the technology. One more thing about the IoT devices and the communication over the GSM is that you can with ease have an GSM model. Many of those SIM 900, SIM 800 chips, they can provide it with ease, the communication for you. They provide the voice communication, they provide data communication for 3G, for sending you via SMS, whatever it is. But the bad thing is about it, like whenever you start your device and you want to join to the network, which is common in IoT scenario where you sleep for a time, then you wake up and you send some data and again go to sleep periodically. In case of the sensor networks, then the problem is that you need to use about 1 ampere of current, assuming 5 volts. So it means that you drain your battery with about 5 watts. This is the energy needed to broadcast your existence to the nearby BTSs to let them respond to you, because you never know how far are there. So you do it with the biggest possible power, right? Then once you start to talk, you know how far this device is, depending on the level of the Ripley. So then you can lower the transmission. But this is also the case of the mobile phones. Perhaps you found that when you go to the distant area with your mobile phone you used to use more energy than in case you are in the city. It's natural. When you're in the forest and nearby, there's no access points. I mean, these BTSs of GSM nearby. Then your mobile phone starts to panic. It wants to talk to someone, usually for more than the 1 BTS, like 3 or 4 of them parallel. So it's periodically announcing its existence full power, just to get to the to hit the possibly the towers that are located somewhere, could be 30 kilometers away, right? And you extensively use energy from your battery, so it drains your battery. My personal advice is, when you go for the long trip, like for the forest, just switch off the phone, right? And that's it. If you need, for example, a whole day to the mountains and you have no way to charge, eventually get some power bank with you, because that's going to be drained much faster than in case when you're in the city. Okay. There's also like radio communication models that you can have. In Europe, there are 2 frequencies. It's 433 and A68. The last one, 868, is replaced in Asia and in America by 915. You can have these models from AliExpress. Be careful about buying 915 because it overlaps with the radio, with the GSM communication radios. You can be banned for it, for using this in Europe. Same in 868 in United States. So that's illegal to use it there. Here, there is no protocol. It's just a radio. So whatever you provide, you need to implement all these stacks or the communication way yourself. There is no infrastructure. There are no standards, and it's a very simple point-to-point communication, but sometimes it's good. This is the way that the drones use for the telemetry, pretty frequent. You just send the messages from the drone, for example, its position, its direction, speed, all the flight conditions to the operator and the ground, and that's pretty frequent to use for 868. There are same models that you can have for the IoT. Now, let's go a little bit higher. So we talk about the network level right now. Guys, just a question to you. Just let me know, when were you born? When were you born? Which year were you born?
Man vienkārši divas videokonferences vienlaicīgi.
97.
98.
98, 97. Okay, good. We are talking about the protocol that was actually invented in the 74. In the 1974, they invented that perhaps there will be 2 to the power of 8 computers, which means less than 256 hosts. It was true in 74, but later on people realized that the personal computers are getting more and more popular. So in the 1801, they invented the IPv4 as we know it by now. And IPv4 is 2 to the 32 of the addresses. Not so many, actually. From the point of view right now, as we live, I wonder if you know it or not, but we run it out of the addressing space of IPv4 last December, in 2019. You no longer have any, you can no longer book any subnetwork. All is already taken. Of course, we have this network address translation, which means that your router makes a subnetwork that has a local addressing. It usually starts from 10.00 something or 192.168, right? Something. This is how it works, indeed, and it helps because for every one public IP address, you can have plenty of them in private, but it doesn't work with the IoT. Why? Because you cannot identify directly the devices that are hidden behind the NAT. So this identity principle of the IoT is broken, which means that, of course, the port forwarding works, but on the other hand, if you consider that you have just a single device connected, then you can put all the communication to it. If you have many of them in the NAT, then you need to have a different port for the same service, which is like very irregular and requires a lot of energy to implement it, kind of the database on the public space, just to know how to access the devices that are hidden behind the NAT. Not so easy. So this is not a solution for the IoT at all. Now, Gartner forecasts that there will be around 8.5 billion devices in 2070. That was stated. And now, in the 2021, that's going to be 21.5 billion IoT devices. That's actually much more to the 2 to the power of 32. It's about the 4 billion. It's less than the humans. At the moment, not a single person in the world can have a private IPv4 address. Public IPv4 address. There are not so many. There are more people. So the solution was IPv6. IPv6 was invented some years ago, but the problem is that actually the introduction to the network doesn't come so quickly because there are still many devices present in the IPv4 network, I mean in the internet, that cannot implement IPv6 because they are too old, too constrained, or they even have hardware solutions that were unable to change it for the IPv6. And also, many of the devices cannot implement full stack IPv6, which is pretty complex and requires a lot of resources, particularly the memory. So what I mean here, it's a solution is 6LoWPAN. it inherits from IPv6. It's integrated with the IPv6 like a one-to-one. Just one thing to let you consider: IPv6 is a flat addressing space. So you're not supposed to have any network address translation in this case. It doesn't exist. It is huge enough to let every single device and the person in the world for, I believe, something like 20 or 30 years from now, or even 50 years from now, will be able to hold this requirements. So the regular IP, even IPv6, assume that at the very end you have a star model, like we discussed it previously. You have an access point, you connect devices to it, right? It is not a case in the IoT networks where we are willing to make a mesh network, like a self-organizing mesh network that would be faulty tolerant, that would be able to reorganize its structure as needed, for example, because of interference, because of the failure of some components, and so on. So IPv6 nor IPv4, they are not like an IoT protocol out of the box. They can be used, but it's like a second choice. So moreover, in case of the IPv6, the devices needs to handle routing tables to know how to talk to the nearby actors within a huge network. So you need to keep this ARP list. Your computer has one. You can type in ARP and you will see the list of the communications. In case of you, it's usually dump because you have just an access to the access point. So it's like local, eventually other machines in your network, and your forwarding to your access. But in case of the next step, is pretty complex. So your router has a huge ARP table. It has a huge memory requirements in this case, right? And moreover, you need to have a kind of the manager we called DHCP server that will assign you an IP address, possibly based on your MAC address or possibly on some other, or just randomly. But there is a central controller for it, right? So you have a central controller for routing and a central controller for managing the addresses. Now, you need to know if you want to make it reliably. So, for example, always bind an IP address to the MAC address and make it fixed. Then you need to configure it manually. So you need to provide, okay, this device with this MAC address obtains this particular IP address, and it's always working this way. This way you can backwards identify the device having its IP address, right? Of course, you need to make it yourself. So this is not a good solution for the IP. Now, how the 6LoWPAN works then? Well, from the physical and the media access control point of view, it's standard 802.15.4. That's the one that is for the IoT devices. The three physical layer modes are 20, 40, and 250 kilobits per second. So it's not very, very high, right? It's like a slow network. It's like a UDP-oriented one. By the way, what's the difference between the UDP and the TCP? Do you know, or do you remember? I just unmuted this. Yep.
TCP requires a response that the message is received. Was it? And UDP just keeps sending messages.
Yeah. Okay. Let me explain you maybe this way. If you have a mobile phone, you can call your mom or you can send an SMS. If you call your mom, you open the channel and you hear one another. So you have some like an instant communication, and this is TCP. If you just send her an SMS, even if she replies back to you, oh, I got it, it is like a UDP. What is the generally problem with the UDP is that the messages are sent and forget. It means that if you send a message and forget it, they can be routed between different routes, and the receiver not necessarily receives them in the correct order. Well, it cannot happen in case of the TCP. So in the TCP, you have first information when the connection breaks, and the second, you have a natural order of the packets you send. They have to be ordered in this in the way. The way you send is the way you receive it, right? It is not the case of the UDP communication. UDP is connectionless. We call it connectionless, right? So you don't open the communication channel. You just send a message, you put it into the network, and it goes, it travels somewhere, and then it reaches the destination. Of course, the destination can make an acknowledge using same way backwards, right? So you can have it like a higher level, application level acknowledge, not translation level acknowledge. But pretty good, yeah, you were right. This is how it works, more or less. Okay, so just get here. This is designed for 800, 900 megahertz and 2.4 gigahertz, and also Bluetooth Low Energy, like it is. It supports 2 addressing spaces. The full addressing space of the 6LoWPAN is 64-bit one, and there's a limited addressing space for small networks using 60-bit one addressing mode. I will show it to you later on how it works, and you will understand how is it possible to have different models here. But generally, the basic frame size for this communication is just 127 bytes. If you can compare it into the IPv6, IPv6 is 10 times more. It supports unicast, so we can send the messages to all of the IoT devices in your network, and it also sends a broadcast, right? So we can have it this way. It supports IP routing and link layer mesh. This is the standard with the 5 by the end, so same 802.15 but .5, right? Link layer meshes may have many gateways to the internet, so it is not like a case in your in case of the IPv4 or IPv6 when you connect to one router and this one router has a line to your provider. Here you can have like a cloud of the device or actually mesh inside, and they can be connected to the internet in different places. And it's not like a backup connection, like in case of, for example, the fail-safe connections in the critical systems in the IPv6, then they switch from one to another. They just work parallel, right? So out of the box. Now, it uses network auto-configuration. So the device that wants to join to this network, it's not like you switch it on and configure something just to do that. You just switch it on and have to connect itself. It's pretty nice. It has an embedded support for security using AES 128, but also the 64. It's usually implemented via dedicated hardware solution, or eventually the resources in the microprocessor unit. For example, Espressif has one embedded, as well as many of the ARM chips like STM. They have embedded AES coprocessor, cryptographic coprocessor for that. So primary is UDP in this case. Now, assuming full address space, it is unlimited number of the devices. Assuming 60-bit address space, the number of the devices is limited for some 64,000. Theoretically, 65536, but some of the combinations are forbidden, so it's about 64,000 of nodes per single 16-bit addressing space. Pretty enough to do most of the tasks in the IoT world. So now, how it works, how the 6LoWPAN works. From the architecture point of view, here is a 6LoWPAN network. Yep. I hope you can see it here. Now, mind the address. The address here, this 2018 123.4.23 is like a network we use. So you see that all the devices are in this addressing space. Well, here are different, right, because they're in the cloud. But here in this area we have, they all start from 2018 1234, right? And here, all the devices are connecting through some edge router. It can be, for example, the Raspberry Pi. Of course, Raspberry Pi, it doesn't support this 802.15 radio. You need to have a special interface to implement it. You can have it from the Texas Instruments, for example. But if you go into the Bluetooth implementation of the 6LoWPAN, that will work out of the box. So just to coming back to this device. This device is an interface between the IoT network and the regular internet network, which is here. So its purpose is just to route the messages forward and back, double ways. Now, if you look into the addressing space, those devices that are here, they have this 16-bit addressing space. So it's just simplified addresses. Some of them are just hosts. So host is something that generates, it's like a leaf in the tree. It just generates the data or receives the data, but it doesn't route the data. but also routers. Don't think about the routers like they're just a single-purpose devices. The routers are usually also the sensors, right? I mean the sensing devices, so or actuators. So your door, by opening the door, closing the door, can also route the messages from other components in the network. This is how the IoT network works. Now, this router, when some message comes from the IoT network to the internet, it's responsible for adding this front part that is missing in the address space here of the devices, just to add it to the frames and then forward it to the regular internet. While opposite, it just extracts this front part, takes a look only on the very last one, and just sends a message back, sends the frame back to one of those devices that are located here in the IoT network. So I guess more or less that you get how it works and how it looks like. Now, the IP router here, the edge router, it can also forward the messages to the IPv4 network. So that's a little bit more complex because it requires like a one-to-one translation, but it's still possible. There are such devices. And there are two ways to do that. The first is just to convert IPv6 to IPv4. And so it's usually done the double steps. First, 6LoWPAN to IPv6, and then you switch it to the IPv4, or eventually you can tunnel IPv4 over IPv6. IPv6 over IPv4, like encapsulate it and send it to some other IPv6 network, or eventually some other IoT network when it's distributed one. So many scenarios are possible here. Okay, so how the 6LoWPAN network starts? Well, there are three steps that are being repeated. The first is something we call commissioning. You establish connectivity, so this is the link layer between the nodes. The next step is bootstrapping, so we perform address configuration, discovery, and the registration. And finally, you initiate routing. So the devices agree how to set up routes to send the messages usually towards the gateway, but not necessarily, because you can, for example, talk to some other node which is located in this mesh network, while you don't route it outside. You just route it internally between the devices. It's similar like you have in your network, for example, now your friend, which is working at home on another laptop, and you send it locally some files instead of going through the Google Cloud, right? There is a number of the things you need to do when you want to add a device to the network. In the regular IPv6 network, the discovery works the way that you just make a kind of the flute. You make a broadcast saying, I'm new here, I want to have an IP address. This is how it happens also in the IPv4, right? So there's a router waiting for you and responds, okay, I can hear you. Here is your IP address based on your MAC. In this case, it doesn't work this way because there is no central router that has a list of the MAC addresses and the IP addresses of this local network. It works a different way. We call it network discovery of neighbor devices. And there are three principles here. First is a node registration. Second is a node commission. And the third is duplicate address detection. How it works? Well, generally, here it's stated on the very low level. But let me tell you the story, just to simplify it. It works the following way. There comes a new device. Let's call the device John for our virtual naming, right? And the number of the devices already constituting the network, some of them are sleeping, some of them are awake. Definitely the edge router is awake, and some other routers in the networks are awake. So the new one comes, the John comes, and he says, hi, I'm John, I would like to join the network, right? So you send a multicast called this SLLAO. It's like a special frame. It's like a here, right? And all routers, by the router I mean here also this routing nodes, not only just the gateway. They respond with the unicast routing accepted. So I can accept your friendship, right? So there comes a new boy to the town, and all the girls want to hang with him, right? Now, the node here, the John, it selects one router it wants to talk to. And it's usually based on the time of the response, but sometimes, for example, it can be considered the radio level, for example, how far this router is, right? So there are different algorithms here. And then it sends this ARO unicast to the selected router. Now, the router can answer, okay, yep, I'm okay. So we are friends now, we can start talking. But the router can also say, I'm sorry. Meanwhile, you are deciding, I had another boyfriend, right? So there came a Steve also wanting to join the network, and I already hooked with Steve. And I have no time for you to support you, John. Sorry. So we have to find another router. So in this case, it's like a cache full, right? I am already handling other devices. The cache is usually small. It's for the couple of the devices. So the node can serve, the routing node can serve some like just the number of them you can count on your fingers. But sometimes it can be more. It's also possible that at this stage, there will be a duplicate address detection. I didn't tell you that, but every single device in the network needs to have a separate address. There's no DHCP server here that will take care about that one. So how it happens? Well, the address is as follows. The mechanism called DAD works the following way. With the unicast you get from the routers, you have this part of the addressing space. So the router, any router, could be, for example, this one here, the letter R. It will inform the new device what is the general addressing space of the subnetwork. And then this new device is randomly choosing some address, the remaining part. And it will announce, okay, so I will have this address. But now there's a process called duplicate address discovery. What would happen if there's already the device with the same address? It's randomly generated, so the glitch or the collision can occur. The devices wake up and they say, no, sorry, that's mine, that's taken. You have to invent another one, right? So in this case, okay, so the John says, okay, I will change my ID to some other because it's already taken. So I will change it and will send it back to you again. And now my new is this one, right? Then maybe some Agnes will wake up in this network and say, no, it's already taken. You have to randomly choose another one, right? And this process repeats until you find an empty one. What is interesting here is what happens with the devices that were sleeping. If the devices were sleeping and there is a duplicate address detection discovery mechanism, they are supposed all to wake up. So the radio needs to be able to wake up the devices that are sleeping. So that's the reason that when someone new joins, it wakes up everyone. It's like, imagine you're in the hostel in the middle of the night and someone comes, right? Everyone is instantly waked up because he's looking for the empty bed, right? So this is how it works, like more or less. Okay, so in this case, you have this agreement with the new status set. Okay, so your address is unique. You have a friend to talk to, and then it works. Now, the node that joined, actually every node, sends periodically NS. It's like a keep alive. So I'm alive, right? If the router won't answer for it, then the device assumes that the router is dead and starts this process again, just to trying to find out another active router just it can talk to. This is how it works. Okay, so this is more or less, this is the second part that was here. So this is more or less how it works. And the node registration is like finding the routing. So once you are connected to the network, now you need to find a way just to send the data to the internet or how to reach other nodes. So you send, again, some unicast to the router, and this router responds with some other messages, and it provides something we call a router rank. This router rank presents how far is it from the edge router. So this way you can tell what's your position in the network, like an approximate, more or less. For example, you are like 5 hops from the networks, or you are like directly talking to the edge router, or you are somewhere in the middle between them. So this is how it works, right? And generally, on this level, the nodes will try to re-register from time to time to find the better routes. So imagine that the routes actually between this all the devices, they can change from time to time. It's self-adapting, self-organizing. If the device, for example, is overloaded, it can just like break, not to answer the NA request like in the previous one. So your device will try to reconnect, and eventually will also try to find the other roads, right? So this is like a self-organizing network. On the low level, it can do self-organizing. Scary, isn't it? It's like Skynet from the Terminator, a little. Okay, then. So conclusion about the IPv6 and the 6LoWPAN. First of all, it's able to create self-organized mesh networks, right? And they are scalable. Second, it can be a start, but it can be also a mesh topology. Whatever here works. The edge router is just like a router in case of the star topology. It uses small frames, 127 bytes, just to communicate, and the really simple addressing mode of 16 bits, so 2 bytes are necessary to keep your address in this case. It's really small. And it's able to detect address duplication and automatically register to the network. So that's all you need to have to implement your IoT. Now, reverting back what we talked about half an hour ago, if you can recall it, I was telling you how to implement the network in the huge building in the Emirates, 60th floor. This is the way you can do that. I mean, it should be just power on the devices and let them communicate one another, and it will be done automatically themselves. Yeah, so that's pretty small. Okay, so I think I'm done for today. This high-level protocols, we are going to talk about this like next week. This is for the programmers. Today it was boring because it's for the hardware guys, and the next week is for the programmers. So I think that's going to be far more interesting for you. Now I can see that I have recorded this video, so I will share it with you on the RTUs. So I will try to upload it there or share it with link. See how huge is that. Eventually, I will do that some other resources. So thanks for joining me. Happy Easter to all of you, and keep healthy and safe. Don't go for this virus anyway, so you had better stay at home.
Yes, thank you very much.
Thank you.
Yeah, you're welcome. Bye-bye.
Bye.
All right. Goodbye.
Done.